So we had some videos going over some basic exponential equations and some basic logarithmic equations. I just have this third video to show you some different types of exponential and logarithmic equations that could come up. And the two exponential ones that I give you right here are actually simpler than the basic exponential equations, honestly, because you don't even necessarily have to use logs in these. Because if you just think about what the first one here on the left is saying, it's saying that 2 to 1 power is the same as 2 to another power. So the only way this is going to happen is if these two powers are equal, right? They must be equal if these two expressions are equal. So all I really have to do here is just set the two powers equal to each other. So I could just say, all right, well, 4x equals x plus 3, and then just solve normally, right? Subtract x, so you'd have 3x equals 3, divide by 3, so you'd have x equals 1. So it's actually very simple because you don't even necessarily need to use logs. Now, could you use logs if you really wanted to? Yeah, sure. You could say, all right, well, I have two exponential expressions here. They're both isolated, so I can immediately just take log base 2 of both sides. So I would just have the log base 2 of 2 to the 4x equals the log base 2 of 2 to the x plus 3. So again, what happens here is inverse property. Those are inverses, they go out, you just get 4x. These are inverses, they go out, you just get x plus 3. So you can still look at it as if it was, using logs, but it's not really necessary to use them. You can just say, all right, I know those two powers have to be equal to each other. All right. Now the second one on the right looks a little bit more complicated, and actually you can get ones that are more complicated, like well you might have like a base of 2 on the left and a base of like 3 or 5 or something like that on the right. And in those cases, those get a little bit more complex because you can't eliminate both both logs simultaneously because there's no way to write one in terms of the other. But in this case, the idea is, you see what I say over here? We have different bases. However, we can express one of the bases in terms of the other, right? And then it'll just be very similar to our first one. So like in this case, we have a 2 and an 8. So when I say express one of the bases in terms of the other, we can really say that 8, right, which is the one base, is really 2 to the third power. So what I can do with this equation here is rewrite it actually then as 2 to the 2x, right? That one didn't change, but now I'm going to replace 8 with 2 to the third. So 2 to the 2x equals 2 to the third to the power x minus 1. And now it looks very similar to just the one that we had on the left over there, where I can say, all right, well, I guess I can multiply those two powers there. So I can say it's 2 to the 2x equals 2, right? Because power to power you multiply, equals 2 to the 3x minus 3. And now I can just do what I did before, right? I have the same base to different powers. So I know that those, and they're equal. So the two powers must be equal. So I would just say 2x equals 3x minus 3. And then solve from there, right? So I'd have negative x equals negative 3 or x equals 3, right? So in this case, I would get 3. And again, I could have said also, like I did in the last one, that I was really taking log base 2 of both sides here. Right? I was really doing log base 2 of both sides, so then I could use my inverse property, and I would still get 2x equals 3x minus 3. But again, it's really easier if you just think of it as, all right, well, I know those powers must be equal. So those were the different exponential ones, and then I also have what I call different logarithmic equations, right? And the writing here is funny because it's such a narrow column that there's like one word per line, and some of the words you see over here combined is on two different lines. It's amusing. All right, but so this first one on the left here, we have the ln of x squared equals the ln of 3x minus 2, and this is just the same idea as the one on the left from above, right? If I have the natural log of something, equal to the natural log of something else, I know that those two somethings, right, in this case, namely the x squared and the 3x minus 2, have to be equal. So I can immediately just say, all right, well, I know x squared has to equal 3x minus 2. Now, the only thing that makes this one a little bit more complicated is it's not linear, it's quadratic. So I'd move everything to one side, so I'd write it as x squared minus 3x plus 2 equals 0, and then I would factor. Well, what multiplies to 2 and adds to negative 3? That would be a negative 2 and a negative 1. So here I would actually get two solutions, x equals 2 or x equals 1. And I just have to make sure that these are both going to work, right? Because remember what we had said about the logarithmic ones? You could occasionally get extraneous solutions that would make you take the log of a negative, which doesn't exist. So if I plug in 2, that's the ln of 4, and that's the ln of 4, so that's good. If I plug in 1, that's the ln of 1, and that's the ln of 1, so that's good. So both those solutions actually work. All right. So again, that was an easier one. And you could have just as easily done the steps with exponentiating. Like I said, you could have just said, all right, well, I'm making each side an exponent of the base e. And again, why base e? Why would I use base e? Because it's natural log, which is the log base e. And then I'd use inverse property, and I'd get to where I was immediately before. Okay? So you can do it either way, but like I say, I think it's easier just to realize that I can set them equal to each other. Now the only one that requires a good amount of work is this last one here, because this last one, the mistake that people make is they say, oh, this is easy, I just exponentiate using base 4. So then they do something like this, which is completely illegal. You can't exponentiate individual terms like this. You can only exponentiate side by side, right? So like if you were going to exponentiate here, you'd have 4 to this whole thing equals 4 squared. And could you do it like that? Yeah, you could. It would actually work if you went through the process. But it's best to realize, hey, this is the difference of two logs. So since this is the difference of two logs, what I can actually do is I can write it as the single log of, remember this from the last section, 9.4, it's really the log of the quotient. So x squared plus 2x plus 1 over x plus 1, right? And now if you notice, if you just look inside the parentheses, x squared plus 2x plus 1 is actually a binomial squared. It's really x plus 1 squared. So I can simplify this thing even more, because now I would be able to cancel one of these with that denominator. So I would really just have the log base 4 of x plus 1 equals 2. So now I did two things. I not only isolated the log, but I also simplified the expression that I was taking the log of. So now it's just the log base 4 of x plus 1 equals 2. And now that I've isolated the log, now I can exponentiate. So now is when I make each side an exponent of whatever that base is, which is 4. So I do 4 to the log base 4 of x plus 1 equals 4 squared, right? I'm making each side an exponent of a base 4. And the idea behind this, again, is over here, these are inverses, they cancel out. So I just have x plus 1 equals, and 4 squared is easy, it's just 16. So then when I subtract 1, I get x equals 15. And that would be my solution to this one, right? So that one actually worked out nicely. Now you might say, well, what if I didn't simplify x squared plus 2x plus 1? What if I didn't factor it and then cancel? It still would have worked. It would have been a more complicated equation, though, that you would have ended up with after you exponentiated. And what would have happened is, I think you would have ended up with two solutions, but one of them would have been extraneous. So it was actually to your advantage if you recognize that x squared plus 2x plus 1 could be factored and canceled, because it made the resulting equation much simpler, and then there was no extraneous solution, right? Because 15 will work if I plug it back into that equation there, right? And then, of course, you could also see ones where instead of having the difference of two logs, maybe that was the sum of two logs, and then instead of being the log of a quotient, it would just be the log of a product. So that's the other kind of equation that could come up there, where instead of having the difference of logs, you had the sum of logs. But it would still be the same basic process. Okay, so those are like the quote unquote different types of logarithmic equations that could come up. All right.